Hi, I'm Mayank Malik, and on behalf of my team, I'd like to introduce you to TorontoLive, Toronto's digital twin running on your desk. Toronto traffic sucks, but traffic, or congestion in general, is a second-order effect. It seems like anything and everything can cause congestion. You can have a train disruption, Taylor Swift could be coming to town, FIFA, it could be bad weather, and it is so easy for us to blame it to the city. I wish Toronto was managed better. I wish the city did more. I know in the photo she seems to be amused, but trust me, she's frustrated. Although you and I are just thinking about getting stuck in traffic and how awful that is, the city is actually thinking about a lot more than congestion, I assure you. We looked at their org chart, and they have dedicated departments for services that are affected by congestion. Toronto Fire Services, Paramedic Services, Emergency Management, Construction Services, Customer Experience, of course the City Manager's Office. They even have a position for FIFA World Cup 26 Secretariat. The city wants to help, but they have no good solution that can combine their really rich siloed data sets, fuse it with external data in real time, and produce intelligent predictions about congestion and traffic while keeping all of that data private behind their IT firewall. Well, now they do. We are TorontoLive, a super real-time digital twin of Toronto that ingests city data streams, runs continuous simulation, and anomaly detection on device on GB10 chip, and deploys autonomous agents to predict cascading urban failures, including congestion, before they even materialize. The entire system ingests live city data streams or replays batch city data, produces local intelligence. There is zero cloud dependency. Data preparation is 90% of machine learning. We ingest a whole bunch of data from Toronto open data sets and then enrich it with external data sources. We built a really complex 6-layer system architecture to make this happen and make it as easy as possible for the end user and as reliable as our predictions can be. At the bottom, we have the data ingestion where we take in all those data sets. We process the data streams using Apache Kafka. Then we have custom-built cascade propagation model that shows how second-order and third-order effects of a particular event affect the city. This is our CUDA accelerated module, which then goes to the reasoning engine. This is work being done by an LLM. We are using Nemotron 3 Super. Finally, we orchestrate LangGraph agents and then show all those cascading effects in the visualization layer. This is a more detailed view of the architecture for those of you who want to pause the video and see those details. Now let's get into the demo. There is a lot happening on the screen, so to quickly orient your eyes on what's where, on the top we have a system status bar. Over here we have our what if simulator with some easy buttons to click. For example, we can inject an event that there's a Raptors game. We can also inject that there's a TTC strike, or we can have some weather events be injected into the system and run what if analysis of the impact of that particular event on the city's infrastructure. Over here is where you'll see most of the action. This is the live city map. On this side, you'll see all those events being added in the incident feed. At the bottom, we have an LLM-based explainer. So this is going to read through the incidents and the cascading second-order, third-order effects and describe to an end user in plain English on what's happening. We have a forecast timeline. So this is, run the entire simulation in super real time. An evidence snapshot at the bottom. And finally, there's a hardware panel where we show all the utilization metrics of the DGX Spark. So this is the digital twin of City of Toronto. Various departments in the city can use it to run what-if scenarios and see how certain events might impact the city infrastructure. In this case, let's say the State Department is interested in seeing what an upcoming TTC strike is going, how it's going to impact foot traffic and street traffic in Toronto downtown. We'll select TTC strike. Let's say it's of 2 hours only, medium severity. We run the simulation. As soon as the simulations run, you see the GPU utilization went up, data is being processed, and you see the spine of blocked transit lines. At the same time, a forecast timeline is running. At every 1 hour, there's a discrete calculation that's going to combine this with other data sets to see how street traffic is going to worsen because of absence of trains running, and also how the foot traffic is going to worsen because of absence of trains. It was a 2-hour event, so we expect to see the peak of those cascading effects at around 2 hours. We see it's getting worse here, and as time passes and trains start running, that impact should dissipate somewhat. So we're coming up to a 3-hour mark, and we see that now that the trains are running, people are starting to take more trains. On this side, you can see an AI incident brief. So there was a complete DTC network shutdown affecting all 4 subway lines with 149 surface routes. Estimated 1.8 million riders were displaced, and we kind of see that simulation running in this screen. As we add more and more data sets, more and more scenarios become available. We realize the vision of becoming a true full digital twin of the entire city of Toronto. Going back to the slides, we wanted to highlight the NVIDIA AI stack that we use in the project. One, of course, we use Nemotron 3 Super, latest for LLMs, so for the GPU accelerated breadth first search on the Toronto City Graph. We ended up using cuGraph to be able to demonstrate how you can take straight up Python code and be able to parallelize it. And finally, of course, we built the entire thing on GB10. A quick introduction to the team behind the work. Nikita worked on front end and really exciting simulation and the user experience. Dervish worked on the GB10 setup and deployments. Tony worked on a video processing feature along with some data visualization work. Andy worked on data processing and event cascading, and I developed the concept, the backend scaffolding, and the NVIDIA AI stack. In terms of next steps, we want to expand the number of scenarios that we support in the digital twin. The true power of the digital twin is to simulate a variety of scenarios from various government departments, be able to combine all of those different data sets and see how they affect each other. For data injection, we want to, of course, allow the highest quality real-time data that we can get to be injected into the twin for improved simulation results. Here's a concrete example of what enhancements look like. One of the things that we started working on already but weren't able to fully integrate into our UI was to ingest real-time feeds from street cameras, and this would help us refine our congestion modeling, for instance. I think the hardest part of this project was understanding the data and working with it. The NVIDIA AI stack was, pretty easy to work with. So we've listed a couple of things that we ran into that ended up taking a lot of time. Some data feeds were dead. For instance, GTFS static data comes as a zip and had to be converted to GeoJSON. The Open Data Toronto Python SDK has no Arch 64 wheel. The Rapids CUDA 12 image is no longer there. And finally, there was a version discrepancy between LangChain OpenAI and the OpenAI SDKs, and we had a hard crash at import time, so we had to figure that one out. With that, I want to conclude this by saying thank you to the entire NVIDIA team, the organizing team of the hackathon. Happy to take any questions. We are going to be around.